If you wanted to build a bridge between two separate islands, you wouldn't just throw bricks into the water and hope for the best. You'd need a specific mechanical process to bind them together. In the world of organic chemistry, constructing complex molecules faces a similar challenge, especially when we want to link two benzene rings together. These rings are notoriously stable and satisfied on their own. So, how do we force them to connect? The answer lies in a classic transformation known as the Fittig reaction. Let's look at our starting materials. On one side, we have an aryl halide. Picture a hexagonal benzene ring with a halogen atom, like chlorine or bromine, hanging off one side like a loose handle. Now, imagine we have two of these molecules. Left to their own devices, they'll simply float past one another. But notice what happens when we introduce a very reactive guest to the party, metallic sodium. As we add the sodium, a vigorous reaction begins. Let's visualize what's happening at the atomic level. Each sodium atom is eager to get rid of its outermost electron. It sees the halogen atom on the benzene ring and essentially offers it a better deal. The sodium pulls the halogen away to form a salt, like sodium bromide. This leaves our benzene ring in a very desperate, unstable state. It's now an aryl radical or a sodium organometallic complex, depending on which pathway you follow. But the result is the same. The ring now has an open, highly reactive bond looking for a partner. And here's the key insight. Because there are many of these reactive rings being formed at once, they find each other. Watch as two of these activated rings collide. The open bonds snap together, forming a new carbon-carbon single bond. This creates a biphenyl, two hexagonal rings locked in an embrace. But wait, why do we use sodium specifically? And why do we perform this in dry ether? If even a drop of water were present, the sodium would react violently with the water instead of our aryl halides, likely ending in a literal fireball. The ether acts as a protective, non-reactive sea that allows the sodium to do its job safely. You might be thinking, this looks a lot like the Wurtz reaction, and you'd be right. If the Wurtz reaction is for linking straight-chain alkanes and the Fittig reaction is for linking rings, combining them gives us the Wurtz-Fittig reaction, which lets us attach a straight chain to a ring. The Fittig reaction isn't just a lab trick. It's a fundamental lesson in chemical motivation. It shows us that by using a highly reactive middleman, in this case, sodium, we can persuade even the most stable structures to reach out and connect. It reminding us that in chemistry, as in life, the most enduring bonds often require a little bit of shared instability to get started.